Okay, so now that we have a definition for what it means to compose two functions, I want to look at some examples, right, and see how we can actually do this first with just some kind of abstract theoretical examples, and then we'll look at some practical physical situations where this can apply. All right, so first I've got two functions here. F of x equals x squared plus 2, and g of x equals x plus 1. And I want to find their composition, f of g and g of f. So let's start with f of g. F of g, and I'm going to write this out a little more completely here. F of g of x. This is equal to f of g of x. Well, that's what composition means, right? The right-hand function gets substituted into the left-hand one. All right, so let's see. This is f of g of x. G of x is x plus 1. And you know what this means, right? Because we talked about functions already. This means replace all of the x's in the f function with x plus 1. Right, and if I do that, I get x plus 1 squared plus 2. And now I can do some simplifying. X squared plus 2x plus 1 plus 2, which is x squared plus 2x plus 3. Right, now let's try the other one. As a matter of fact, we want what? G of f of x. You can go ahead and pause this if you like. Try working that one out on your own, see what you come up with. Then come back and watch how I do it. All right, so first I'm just going to use my definition. This is G of f of x. And f of x, that's x squared plus 2. And now if I go to the g of x function and replace that x with x squared plus 2, I get x squared plus 2 plus 1, which is x squared plus 3. And there's my answer. But I want you to look at these, right? I want you to compare these two. And notice that they are not the same. F of g of x does not equal g of f of x. All right, so more specifically, when you use kind of the right technical language here, function composition is not commutative. Or to put this in more practical terms, the order in which you compose two functions makes a difference. Sometimes there will be situations, we'll talk more about that in a little bit, where they are the same. That is a possibility, but it is not guaranteed, right? It's entirely possible that they will not end up being the same. All right, so now I've got a practical example, right? We're purchasing a car, and we have an option of two discounts. Right? One is a flat $300 off the price, and another one is where you only have to pay 95% of the price. In other words, it's 5% off. All right, so what I want to do here first is I want to come up with two functions that describe the final price in each case. All right, so let's do the $300 discount first. Right, for that one, let's call this P1 of x, where x is the list price, and this P1 is the final price. All right, so how do we get the final price in this case? Well, we take the list price and subtract $300. Just simple enough. Right, now let's do a second function, P2 of x. This will be the percent discount. And to get the final price here, we take that list price x and multiply it by 0.95. All right, so there we've got our two functions. All right, so hold on to those. All right, hold on to those, and let's see how we can bring this idea of function composition into this example. All right, so I've got the exact same two functions. Right, let me write them again here. P1 of x is x minus 300, and P2 of x is 0.95x. And now the thing I've added here is you are such a dazzlingly good negotiator that you have convinced this salesperson to give you not one discount, but both of them. All right, so I want to come up with a new function that describes the new final price based on getting both of these discounts, one discount and then the other. All right, so how are we going to do this? Well, how would you do this in practice, right? Just think about how you would do this in numbers. If the car was $30,000, what would you do? Well, you would start by calculating P1 of 30,000, and you would get a number, and then you would calculate 95% of that. In other words, you would take this number and put it into the second function, and then you would get your end result, the actual final price after both discounts. Well, you see how this is matching our composition situation. I'm taking the result of one function and putting it into the other one. All right, so let's give that a try. All right, let's call this P sub F for P final. Right, and this is going to be P1 composed with P2. All right, so well, what is this? This is P1 of P2. P2, that is 0.95, so this is P1 of 0.95x. If we put 0.95x back up into the P1 formula, we get 0.95x minus 300, and there's our new formula. Maybe, right? Maybe. Because remember, we talked on the last slide, right? When you're doing function composition, I said from a practical perspective, the order you do the composition matters. All right, so let's try this again. Matter of fact, now I'm going to have to change my name, though. Let's call this P sub F1. And let's come over here and do this again. Let's calculate P sub F2, and this is going to be P2 of P1. You can pause this, right? Pause for a second. Try working this out yourself. See what you come up with. All right, so this is going to be P2 of P1 of X. P1 of X is X minus 300. All right, so put that X minus 300 into the P2 formula. And this is 0.95 times X minus 300. And then you can distribute that 0.95. So this is 0.95X minus 95% of 300. That is, let's see, 10% of 300 is 30. Half of that is 15. So I'm thinking 285. So yeah, we did get different numbers. Right? We did get different results. So it matters as you're negotiating this deal, right? It matters which of these discounts gets applied first. Right, now the question I always ask when I'm doing this in a ground class is, which of these is better? Right? Which of these is better? And students, they always look at this and say, well, look, they both start off with this 95% off. Then one subtracts 300 where the other subtracts 285. So the only real difference in the end result is that subtraction bit, and the PF2 one subtracts less. So students always come back and say, okay, this PF1 option is better. It's better to do the percent first and then get the discount. And I always remind them, perspective matters. Right? If you're doing this as the customer, as the buyer, yes, PF1 is better. However, if you're the salesperson, right? If you're the salesperson, then you want to come across as the good guy. You're giving them both discounts, but you still want to maximize your profit, right? You still want to maximize the price. So from the salesperson's perspective, PF2 would be the better option. Right, so I have another example here, right? You can pause this if you like and try to work this out on your own, right? Where we've got a similar situation where we have two things being done to the list price, right? First, there's a $20 fee, a flat $20 being added for shipping, and then there's a sales tax being added, and I want to calculate the total cost after both the fee and the shipping cost are added. And you notice there's a little bit here at the end, right? You're trying to find the total cost, assuming that the delivery fee is taxable. And it's that bit right there that's telling you what the order is. Right, so you can pause if you like, go ahead and try and work this out, then jump back in and we'll go over it together. Okay, so we have two functions here, right? Cost 1, C1 of x, whoops, excuse me. Got my notation a little mixed up. Don't need the equal sign yet. C1 of x will be x plus $20. And C2 of x is x, or it's 1.075 times x. That's the original price plus the 7.5% sales tax. Okay, so now we want to come up with a function c of x. That'll be the total cost. And what order do we do these in? Well, remember we said that you have to do you have to add in the shipping cost first and then add the tax, so that both the price and the shipping have the sales tax applied to it. So now here you have to think for a minute. Remember, this composition, it kind of goes in reverse order. The function that goes second is on the outside, and the function that goes first is on the inside. So that's how I'm going to write this. And then if we immediately just rewrite this with the function notation, this is C2 of C1 of x. And I think it's a little clearer here that because you're so used to working inside parentheses first, right? So here I think it's clearer that the shipping is being added and then the sales tax. All right, so let's finish this up. This is C2 of 1.075x, which is 1.075 times x plus 20. And then we can distribute this. This is 1.075x plus 20 times 1.075. And then we can clean up that number. 1.075x plus, what does this come out to? It's going to be 20 plus $1.50? $21.50? Okay, so I'm doing this in my head. So if I mess that up, you're welcome to get your calculator out and double check me. But I think that's what it's going to come out to. All right. So what's next? Well, we're still in a sense talking about functions, and when we talked in the series of lectures where we were explicitly talking about functions, finding the domain was a pretty big deal. Right, so that's where we're going to go next. We're going to talk about how you can find the domain of the composition of a composite function.